and welcome to the Experimental Design Workshop. My name is Joseph, and I'm one of the lead STEM tutors here at the Academic Resource Center. The aim of this workshop is to help you all become better investigators of the natural world using the scientific method. In service of that broad goal, we will briefly discuss what science is and how it is done before launching into some practical exercises to apply these methods. If you'd like to get the most out of this workshop, I'd highly recommend downloading and printing the handout available on our STEM resources page under the Workshops tab. First, what is science? I found this definition pretty practical. Science is the pursuit of understanding of the natural world, following a systematic methodology based on evidence. So, why do we do science? To understand. To understand what? The natural world. How do we do this? By following a systematic methodology, or a formal process, in other words. What kind of methodology? Well, that's answered by this list on the right. Underpinning all of this is a trust that our five senses can be used to learn objective truths about reality. We employ our senses to observe things in nature, and then, using our observations as evidence, we argue for some truth about our world. Over the centuries, scientists have refined this idea into a process that is used by all scientists in their pursuit of knowledge. Truthfully, reality isn't quite as neat as that. There is some difference of opinion among scientists as to exactly what they do and how they do it. This source that I have on screen at the moment attempts to list some general principles that all scientists adhere to. This alternative list was created by a committee as part of a framework for teaching science. Notice that although it differs from the previous one, most of the same ideas are present: investigation, explanation, argument, etc. Once again, this diagram was created based on the survey responses of about 50 scientists. It envisioned scientific inquiry as a cycle of asking questions, finding answers, and repeating. We again see common ideas of observing, questioning, explaining, and communicating. The scientific method, however, is the best attempt so far to distill and formalize how science is done. It's simpler than some of the examples I showed a moment ago, because science is fundamentally simple, though simple doesn't necessarily mean easy. The first step is to make an observation about the natural world. This requires curiosity. Albert Einstein once said, "I have no special talents. I am only passionately curious." I'm gonna have to disagree with Einstein here, because I think passionate curiosity is a special talent. For instance, has anyone ever seen a rainbow pattern like this one on the pavement in the top right of the screen? Have you ever wondered what causes it, or even given it a second thought? There's so many fascinating and beautiful phenomena in our world, but we rarely pause or ponder or investigate them. The next step is to ask a question. Asking good scientific questions is a skill that can take time to develop. Some of us used to be great question askers when we were young, but later became discouraged. Now that we have an observational question, and before we start experimenting, we first speculate about how we could explain the observation. This possible explanation is called a hypothesis, and often answers why type questions. Finally, we create an experiment to test whether our explanation was correct. This step requires creativity, tenacity, and even some luck, and it's the most exciting part of the process. Now that we've gained some knowledge about the world, we can then use that knowledge to ask new questions and repeat the process. Here's a silly example of how the method can be applied. First, we make an observation. In this case, we're talking about a toaster, and our observation is that the toaster won't toast toast. You had one job, and you can't do it. This leads us to ask a question. Why won't my toaster toast toast? What hypotheses can you think of to explain the toaster's behavior? That is, what do you think might be wrong? Go ahead and record your hypothesis on your handout. So after you've done that, I will note that there is not just one correct answer. There are many possible hypotheses, including maybe there's a broken wire in the toaster, maybe the bread was frozen or the wrong type, maybe the outlet that the toaster is plugged into is broken, maybe the timer setting was too short, etc., etc. So if you wrote down any of those or any others that you came up with, you're probably on the right track. So let's just pick one of these hypotheses and use it to make a prediction. The comic decides to hypothesize that the outlet might be broken. How might we test this hypothesis with an experiment? Or if you wrote down a different hypothesis, how might you test yours? Write down your response on your handout. The comic makes the prediction, if I plug the toaster into a different outlet, then it will toast the bread. We now have a question, a possible explanation, and have designed an experiment to test it. The only thing left to do is to actually carry out the experiment. What steps might you follow to carry out your experiment? You can write those down in the fifth box. For this simple experiment, we merely plug the toaster into a different outlet and try to toast again. Now, one of two things happens. Either our hypothesis is supported. Now, note that doesn't mean it's proven, but supported, or it's not. Either way, we have learned something, and we can now ask new questions. On your handout, briefly write down two new questions. One for if your hypothesis, or I'm sorry, if your experiment had supported your hypothesis, and one for if it had not. What new questions did you come up with? The comic comes up with two questions. Either the change in outlet supports either the change in outlet makes the bread actually toast, and so that supports the hypothesis that there actually is something wrong with the outlet. So that leads us to a new question. Well, what is wrong with the outlet? Why is no power flowing? Or if the bread still won't toast, then maybe we speculate that there's a broken wire in the toaster, and that might lead us to a different set of experiments. So you see this does lead to iteration, and it is back to one of the slides that we showed previously about science being a little bit of a cycle. All right. So now let's practice with something a little bit more tangible. This is a pendulum. It's a physicist's favorite toy. It consists of a heavy weight hung from the ceiling by a thin, light string. Most of us were once children, so we're familiar with playground swing sets and yo-yos, and we can predict how this object behaves. But even this familiar system might hold some surprises. When we move it a bit from its resting position, it tries to return to where it started, but it overshoots and starts oscillating back and forth. This system is so fascinating because this oscillatory behavior appears all over the place in nature. By understanding the simple pendulum, it helps us better understand everything from subatomic particles to light waves to brain functions to the motion of planets. We have already observed the behavior of this system, so let's begin asking questions. Now, it turns out that one especially important question is, how long does the pendulum take to make one full swing and return to its starting position? We call this time interval the period of the oscillator. What are some things about this pendulum that we could change to alter the time it takes to complete a swing? What are some physical variables that we could adjust that might affect the period? Go ahead and write what you think down on your handout. So again, just for examples, we could change probably the mass at the end of the string. We might change the length of the string. We might change the initial angle or initial displacement. Or maybe we could change the strength of gravity. Any of those things, and possibly others, are different variables that might affect the time it takes to complete one full swing. Now, let's come up with a hypothesis. What do you think will happen to the period if we increase or decrease the variable that you chose? Record your observations and hypothesis in the first few boxes on your handout. All right, so just a quick recap of what we have so far. This is what we've done to apply the scientific method. The first thing was that we observed oscillatory motion. And next, we asked a question. How is the time to make one swing or the period affected by, and then fill in the blank with whatever variable that you chose? And then we made a hypothesis. We suppose that changing that variable will, and then insert what you think. Will it increase? Will it decrease? Or will it not change the period? So the next thing to do is to design and carry out an experiment. How might we design an experiment to test each of our hypotheses? I'll give you a second to think about that. So while you're doing so, some things to have in mind, some aspects of a good experiment. One thing is a controlled trial. That is, we don't want to adjust more than one variable at a time, because suppose we change two variables and we got an effect, we got a change, then we don't know which one of those variables, or possibly the combination of them, actually caused that change. So we try to isolate one at a time and test one at a time. Also, think about how you might quantify your uncertainty. And that's a fancy way of saying we can't ever measure things with perfect precision. For instance, if we're measuring the period of this oscillator, we might use we might get an answer in seconds. And suppose we measure the period and get, say, I don't know, 20.8 seconds, and then we make some change and we measure it again and we get 21.1 seconds. How can we have confidence that these are the same or different? Is that small difference in time the result of just our imperfect reaction time, our imperfect measurement methods, or have we observed a real change in the period? And lastly, we want to think about sources of bias and how we might remove them. So, for instance, maybe if I were doing this experiment in person and I had tested this out, maybe I already know what the numbers should be in my head. And so I subconsciously modify the timing with which I start or stop my stopwatch to adjust things to be more in line with what I believe them to be, or what I believe the answer should be, rather than what the experiment actually shows. So we want to think about those things as well as we're designing an experiment. All right. So because we can't do so in person, because this is going to be recorded as a YouTube video, we'll have to rely on a simulation to carry out our experiments. Take a moment to scan this QR code, and that will open a link, and you want to click the option that says Intro. It should take you to a web page that looks like this here on the left. If you can't scan the QR code, then the same link is below the QR code on the slide. All right, so I already have this pulled up in my browser. So here it is. And you can click and drag on the mass to displace it from its equilibrium. And then if you release your mouse, the simulation will begin and it will start oscillating back and forth. So we'll just need to adjust a couple things from the default before we get started. First, because we want to time the oscillations of the pendulum, let's check the box in the bottom left that says stopwatch. That will make this little box appear, and we can drag it around to where we want to put it. And second, to make things a little bit more realistic, let's take the friction slider and move it just a couple ticks to the right. That looks fine. All right, and now let's stop and reset the simulation. All right, so hopefully you've written something down as far as how you would design an experiment. So I'm going to give you my ideas about how I might design an experiment to test the period of this oscillator. So the first thing I want to do is to record a control with all the default parameters, all the default variable values, so that we have something to compare to after we make changes to the system according to our hypothesis. I'd recommend dragging the pendulum out to maybe about 8 or 10 degrees, somewhere in there. Take it about 10 degrees from its resting position, and then let it begin swinging. So the way that I will measure the period is I will let the pendulum reach one of its positions of maximum displacement, so maximum angle, and then I will start the stopwatch. Then I'm actually going to record not one full swing, but 10 full swings. And I'll explain a little bit more why I do that in a moment. So let me go ahead and do that. And the reason I do that is because of my imperfect reaction time. Remember, I was talking about sources of error in our experiments on the previous slide. So because of my imperfect reaction time, every time I start or stop this stopwatch, I introduce a little bit of error because I think human reaction time is somewhere around 200 milliseconds or something like that. So every time I press this button or make an observation, I am introducing a little bit of error. So if I record 10 swings of the pendulum, I can then divide the total answer by 10 to get an estimate, a better estimate of a single period. Okay, I just said a bunch of things. If all that didn't make perfect sense, don't worry. I'm going to go ahead and record this and record this experiment. And I think that once we do the calculation, everything will click. All right, so I'm going to reset this one more time. So I'll take it out to around, let's do 8 degrees. And I'll let it go. And then I will wait until it reaches the maximum displacement and start the stopwatch around there. 1, 2, 3, count with me, 4, 5, 6, 7, 8, 9, 10. All right. All right, so I just recorded 10 swings of the pendulum. So let me go back to my slide here. So I just recorded 10 swings of the pendulum, and the variable name that we use to represent the period is a capital T for time. And so I just recorded that to be, what was it, 16.67 seconds. And then I estimate that my imperfect reaction time adds an error of about 200 milliseconds or 0.2 seconds. So what this plus or minus means is that I believe that my answer could be, or my recording could be wrong by as much as 0.2 seconds in either direction. All right, so now to get the period itself, I can divide by 10, and I get 1.667 plus or minus 0.02 seconds. All right, so that is my control. That is my estimate for the period before changing any variables. All right. So hopefully now that you saw me do that once, it makes a little bit more sense as to how we're running this this experiment. The other thing I want to point out is I created a simple little Desmos graph to help us visualize the data that we're taking. So that is over here. And so this variable E just represents the error. So that was 0.02. And then I'm using the variable T0 to represent the initial period. So that was 1.667, I think. And so here it shows up on the graph And here are our error bars. Okay. All right, so now we have recorded our control. So let's make a change and hypothesize about what will happen when we make that change. So I don't know what you chose. You're welcome to do, I encourage you to use whatever hypothesis you chose and perform another similar experiment. I'm going to choose to change gravity just because this is an online recording and we're using a simulation and not a physical pendulum. And so I can make, and so while trips to Jupiter are pretty expensive, in the simulation, I can just change a little slider and I get an entirely different, answer. All right, so I'm going to make a change to gravity, and I don't know, I just chose Jupiter for fun. Now I want to keep all the other variables the same, and I want to perform the exact same experiment again. So once again, I will drag this out to, I think I did 8 degrees last time, and I will let it go, and I will once again record the period. So this is going a little bit faster, so I might have to concentrate a little more. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, let me stop that. Okay, so now this is my new recorded period. So this was the initial period. So I just recorded 10 swings of the pendulum after adjusting gravity. And I got 10.57 seconds, and then plus or minus I'm assuming that my reaction time is still the same. And so after dividing by 10 once more, I get 1.057 plus or minus 0.02 seconds. Okay. All right. So now, based on my hypothesis, so my original hypothesis was I'm going to change gravity, and I believe that increasing gravity should lead to a decrease in the period, because higher gravity seems intuitively like it should make the pendulum swing more quickly. And so let's actually see, based on our numbers, whether our experiment supports that hypothesis or not. So it can be a little bit difficult to just look at these numbers and tell that they're different. Well, in this case, I think it's pretty clear that they're different, but in your own experiments, you might get very similar results. And so I would go back over to this Desmos graph, and I'll add my new, period that I just measured to this graph. And where did it go? There it is. So, as you can see, even despite our small error, as recorded with this variable e, these 2 points are at vastly different heights, much quite far away. And so, because we recorded the uncertainty, we can have pretty high confidence that we have actually observed a real change in the period of our oscillator. And I believe that our hypothesis was supported. Increasing the gravity did in fact decrease the period. Okay. All right. So that is essentially the end of what I actually want to cover. And hopefully you are able to use these tools, the simulation, this Desmos graph, and to play around with this just like a sandbox and come up with your own hypotheses, your own experiments. And I hope that you have the joy of seeing and actually understanding whether your hypothesis was supported or not. So that is essentially the end of what I would like to cover here. This I have so this presentation is based on many different sources. So if you would like any more information on any of the things that I discussed, I'll leave this works cited page up for just a second, so that you can access any of those. And the last thing is thank you so much for your attention. Thanks for attending this workshop. I hope you found it helpful. If you have any questions or feedback, you can you can find our website here at the bottom uh, at brightpoint.edu/services/tutoring, or you can send us an email. Our email is arc@brightpoint.edu. Thanks again,